Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the graph of a hyperbola, plural hyperbolae. So hyperbolae have this equation here. So we're going to graph equations of this form. So it's really important when we're graphing hyperbolae that we look at the domain and range, the values that x and y can take, because it turns out there's always a value x can't take and always a value y can't take when you have an equation this form. So domain, values that x can take. So let's look at this function here. What are the values that x can't take? Well, we're dividing 2 by x minus 1. Division becomes a problem when you divide by 0. I can't divide 2 by 0, doesn't exist. So this will cause a problem if the denominator is equal to 0. So the denominator will equal 0 if x is 1. Any other value is fine. You can divide 2 by any other number except 0. That's the only problem. So x can take any value except 1, and this is how we write the domain properly. We write it in these squiggly brackets because it's a set of values. We write x such that x does not equal 1. So this just basically says x can take any numerical value except 1. It's the set of all numbers excluding 1. Similarly for the range, there's a value that y can't take. Now this fraction here can never equal 0. You can never divide 2 by something to get 0. So if this can't equal 0, y can't equal 0 plus 3. So y can take any value except 3. So the range, the set of values y can take, is any value except 3. This is how we write it properly. So why is that really important? Well, it turns out hyperbola have these things called asymptotes. So asymptotes are no-go zones. They're parts of the Cartesian plane the graph can't hit. So we just figured out that x does not equal 1. X can't equal 1. So I'm going to draw a line here at x equals 1. When I draw the graph of this function here, it cannot hit this line. Similarly, I need to draw the line y equals 3. The graph cannot hit this line either because y cannot equal 3. So it turns out for hyperbola, they always have a characteristic shape. What they do is they get closer and closer to the asymptotes, but never actually hit them. So that's what an asymptote is. It's a line that the graph gets closer and closer to, but never actually hits. So for this, you'll probably need to find a couple of points on either side of the asymptote just to help you. So to find a point through which this graph goes, just substitute any value you like for x, other than, of course, x equals 1. So let's substitute x equals 2. So if x equals 2, then y equals 2 over 2 minus 1 plus 3, which is 5. When x equals 2, y equals 5 from this equation here. So this graph goes through the point 2, 5. So similarly, we can pick a point over here. Let's just pick, for example, x equals 0. That's a valid point here. So if x equals 0, y is equal to 2 over 0 minus 1 plus 3, negative 2 plus 3 is negative 1. This actually goes through the point 0, negative 1. Now remember that this graph cannot hit this line or this line. So what it's going to do is it's going to go through this point. It's going to get closer and closer to but never hit this asymptote. It's going to get closer and closer to but never hit this asymptote. Similarly, it goes through this point here. It's going to get closer and closer to this asymptote and never hit closer and closer to this one. So this is what the graph looks like. The graph for hyperbolae always have these weird shape. They're always in two parts. It turns out because this number was positive, the graph lived in the top right and bottom left of the quadrants defined by the asymptotes. All right, let's now look at another example. So let's look at graphing this equation here, y equals 2 minus 1 over x. Note that this is the same as the graph of negative 1 over x plus 2. So in this case, x cannot equal 0 because you can't divide by 0. So x equals 0, which is actually the y-axis, that's an asymptote. That is a no-go zone for this graph. Similarly, y cannot equal 2. It's always this constant that y can't equal. So I'm going to draw an asymptote along y equals 2. So what this picture is saying up here is what I said on the previous slide. If a, which is this number on top of the fraction, is positive, then the graph will be in the top right, bottom left of the quadrants of the asymptote. But if a is negative, the opposite. It'll be top left, bottom right. So in this one here, because this is a negative, a is actually negative 1. So a is negative, meaning the graph is going to live here and here. It's going to be in two pieces. So you can probably tell it's going to go like that, closer and closer to its asymptotes, and then down there. But you might need a point to help you know exactly, does it go here, does it go there? That's fine. So let's pick a point in this quadrant here. Let's pick x is equal to negative 1. So if x is equal to negative 1, y is equal to 2, minus 1 over negative 1, 2 plus 1 is 3. So negative 1, 3 is this point here, and then we can pick a point in this quadrant here. Let's just pick x is positive 1. So if x is positive 1, y equals 2 minus 1 over x, which is 1. 1, 1 is this point here. So the graph is going to get closer and closer to, never hit its asymptote. It's going to go like this. And then down here, it is going to go like this, closer and closer to, but never hitting its asymptotes. All right, let's look at a harder example of the equation of a hyperbola. So this equation might look like it's not of the right form, but we can easily make it in the right form. See, what we're going to do is we're going to replace the top with x minus 5 plus 5. Why am I doing that? Well, x minus 5 plus 5 is x. So these two expressions are equivalent. So because of the way fractions work, I can split up this fraction into x minus 5 over x minus 5, which is just 1. So what I have here, I have this thing which is 1 plus 5 over x minus 5. So this equation here is the right form for a hyperbole. So this would have asymptotes at x equals 5 and y equals 1. So I just wanted to show you that the equation of a hyperbola is sometimes written a bit differently. All right, let's look at one final example where we find the equation of a hyperbola. So I'm going to find the equation of this hyperbola here. I know it's going to take the form y equals a over x plus b plus c. So all I need to do is find a, b, and c. So it turns out we can find b and c really easily from the asymptotes. So the x asymptote, the value that x can't take here, is minus 1. So b is actually going to be positive 1. It's always the negative of the value of the asymptote that goes down here. And that's because negative 1 is the value that makes this expression equal 0. It's always x minus the value of the asymptote, x minus negative 1, or x plus 1. This one behaves the way that you would expect though. The y asymptote is at 1, so c is going to be 1. In this case, it's positive 1, okay? So this equation is consistent with the asymptote. If you substitute x equals minus 1, you get a problem because you can't divide by 0, and you can't have y equaling 1 because this can never equal 0, so y can't equal 0 plus 1. All right, now we only need to find a. So to find a, similar to what we did for parabolas, we're just going to substitute in a point that we can clearly see. So a point that we can clearly see here is at negative 2, 3, or this one, 0, negative 1. It doesn't matter which point that we use. So let's use this one here, 0, negative 1. So what I'm going to do to find a is I'm going to substitute x for 0 from that point, and we're going to substitute y for negative 1. So this is a very easy equation to solve. We're going to subtract 1 from both sides. Of course, a over 0 plus 1 is just a over 1. We get a equals -2. So the final equation is y equals a over x minus the value of its asymptote, x minus minus 1, which is x plus 1, plus the value of the y asymptote. And that's our final answer. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.